Welcome to Study Loop.
Okay, so we're going to do chapter 29, problem 5. So this problem says there's a circular loop of wire with a radius 12 centimeters. So r equals 12 centimeters. This is in the xy plane. So let's call this x, y, and z going up. Okay, so it's in a uniform magnetic field. A field of 1.5 teslas is directed along the positive z direction. So E equals 1.5 Tesla pointed up. So B equals 1.5 Z in the Z direction. Awesome. Okay, so part A asks if the loop is removed from the field region in a time interval of 2 milliseconds. So delta T equals 2.0 milliseconds. Find the average EMF that will be induced in the wire loop during the extraction process. Okay, so this is a Faraday's law question. So we're going to use Faraday's law, and that says that the EMF, the average EMF, is given as the negative change in magnetic flux over the time interval. Okay, so now we got to figure out what our magnetic flux is. So our magnetic flux initially is just B times the cross-sectional area, right? Okay, so, and then finally we're completely removed, so this is 0. So if we're looking for the change in flux, this is the final minus the initial, so that's given as negative, and then we have final, which is 0, minus B times pi r squared. This is all over delta T. Okay, so awesome. Let's calculate this out. We see these negatives are going to cancel, so we're left with 1.5 teslas times pi times 12 centimeters squared all over 2.0 milliseconds. So if we change these back to SI units, and this becomes 1.5 teslas times pi times 12 centimeters, or 0.12 centimeters, 0.12 meters. 12 centimeters is 0.12 meters, all over 2 times 10 to the negative 3 seconds. And put this in our calculator, and it comes out to 34 volts is our average EMF. Okay, so part B asks, is our current counterclockwise or clockwise in our loop? Okay, so if our initial B field is this, our final B field is 0. That means the change in flux is pointing down. So when we're inducing a current, we want the current to oppose the change, because we're always wanting to oppose some change that is happening. Like when you push on something, it pushes back. That's what we kind of want to think about. So if our magnetic flux is going from a very high in this direction down to 0, that means the change in magnetic field is pointing this downward here. Okay, so that means what current would a counterclockwise current produce a field upwards or downwards, and would a clockwise produce a field upwards or downwards? Since the change is pointing down, whichever one is up is the current that we're inducing. So that means if using the right hand rule, you should see that a counterclockwise current would produce up. That means so is induced, since we need the current induced to oppose the change. And a counterclockwise current in this loop would produce a upward magnetic field using the right hand rule. Awesome.